Welcome, I'm Giorgio Saracco, and today I will give you a full characterization of isoperimetric sets in 2D domains that satisfy some topological assumption and some structural assumption that I generally call to be without nex. The talk will be split over two videos in part 1 and part 2 in this brief outline. In part 1 I will introduce the problem and quickly review what the perimeter is, give you some of its properties so you have a somewhat clear idea of what we're talking about, and quickly discuss existence, which is more or less for free. And then I will start tackling the core of the talk, that is the shape of the minimizers. And this will take the second part of the first video, and will be the main topic, say, of the second part of the video. And finally, I will briefly talk about some convexity properties that we basically obtain as a side effect of our main results. So, without further ado, let me present you the topic. That is the following: we take an open-bound set omega, say in general in the n-dimensional Euclidean space, but later on I will restrict myself to the two-dimensional space, and we define the isoperimetric profile as the functional that to each volume V in between the 0 and the volume of this open-bound set omega, that I will sometime call the box, associates the least perimeter needed to enclose the given volume among subsets of omega. That is, I'm looking at the infimum of the perimeter E among all subsets of omega whose volume is given by V. Now, by volume or mass, I mean the usual n-dimensional Lebesgue measure, and by perimeter, I mean the variational perimeter, which is also known as distributional or Cacciopoli or de Giorgi perimeter. And okay, the main questions are the following. Do isoperimetric sets, that is, minimizers of this functional, exist? If they do, what is their shape? And can we tell something about this function J? And I will show you that this function is actually has some convexity properties. Now, before starting, let me give you a sort of definition of what perimeter is. Now, you may have a naive idea of what perimeter is, that is the n-1 surface measure. And this is right whenever your set is regular enough, say Lipschitz. Okay, if your set is less regular, the perimeter is something else, but basically we can think of this perimeter function as the lower semi-continuous relaxation of the n-1 dimensional Hausdorff measure of the topological boundary, so that whenever your set is regular, again, say Lipschitz, then this perimeter coincides with the n-1 dimensional Hausdorff measure of the topological boundary. And, well, as I told you, you can think of this perimeter as the lower semi-continuous relaxation, and thus this perimeter is lower semi-continuous with respect to, say, the L1 topology. So, and by L1 I mean the convergence of the characteristic functions of the sets. And the other good thing is that any sequence of sets with equibounded perimeter is precompact. That is, you can extract a subsequence that converges in L1 lock to a set of finite perimeter. And basically these two properties, 2 plus 3, immediately imply existence. And this is more or less a standard exercise of applying the direct method of calculus of variations, that we will immediately see how it works. And this is more or less why I say that existence is trivial, because it basically follows from the properties of the perimeter functional, and this is more or less the full proof. So you fix a volume, and you assume that the isoperimetric profile is finite in that point, because if it is plus infinity for all competitors, then really you have nothing to do. Well, then the functional is clearly bounded from below by 0, because if the perimeter of any set is always non-negative, and thus you can pick a sequence of sets such that their mass is fixed and equal to the volume, and their perimeter converges to the value of the functional evaluated at this volume V. Now, by compactness, well, it is easy to see, since you have this converging sequence, it's clear, it's very easy to see that it must be the perimeter of these sets must be bounded from above, okay, uniformly, and thus by compactness you can extract a converging subsequence in the L1 log topology. And well, since the sets are all contained in this box omega, you really get, you improve to the, say, global L1 convergence, so you don't lose mass, okay, so that your limit set E has the same volume of the volume of the as the same volume of the sets in the sequence, okay? And then you just use the lower semi-continuity of the perimeter function, and you discover that the perimeter of this limit set is less than or equal to the lim-inf of the perimeter evaluated for sets in the sequence, but this is exactly the value of the functional, of the isoperimetric functional. And this implies that this limit set E is a minimizer, and this basically settles existence. So this is very easy, and somewhat this sort of proof is somewhat the standard proof one uses when it deals with functionals, say, governed by the perimeter, okay? So the real interesting question is, okay, we know there are minimizers. Who are they? What's their shape? Okay, and well, from now on I will restrict myself to dimension 2, and there is, say, a technical reason, but okay, I also know that most of the results I will present are false in higher dimension. We do have counterexamples, and I will make clear why we need dimension 2. There is a very specific result that basically hold only in dimension 2, and that allows us to make all our constructions. And well, okay, by the isoperimetric inequality, if your volume is small, that is smaller than or equal the volume of the greatest ball you can fit inside your box omega, so is smaller than or equal pi times capital R squared, where I set capital R to be the radius of the greatest ball inside omega, well then, this is just the classical isoperimetric inequality. Minimizers are both. So the true challenge is to characterize minimizers for higher volumes, for greater volumes. And well, the bad thing is that the functional J is nasty. And this is because it has a volume constraint, which is not very easy to deal with. So the idea, the strategy we will employ is to find minimizers of a different problem, of an auxiliary problem, and well, we shall actually prove that we can then find all isoperimetric sets minimizing this auxiliary problem for some suitable choices of parameters, okay? So the auxiliary problem is going to be this one. We're going to fix some positive constant kappa, and we look at the following energy now. You will have perimeter E minus some volume term, which is minus kappa times the volume of E. And we will minimize this functional in a class of competitors where the constraint is relaxed, okay? So we will not anymore ask the volume of the competitors to be fixed and equal to V, but something less. And this will make our lives much easier. And okay, so this is more or less the strategy. And let me start with this, say, remark. Assume that we're trying to minimize this energy, so the perimeter of E minus kappa times the volume of E, among all subsets of omega. Okay, so no constraint at all aside being a subset of your box omega. Okay, then as just you can use the same proof as before and you can prove you have minimizers. Okay, it's the exact same proof basically. And well, take a minimizer E, then E is also an isoperimetric set for its own volume, and this is because it is minimizing this energy perimeter of E minus kappa times the volume of E among all subsets of omega. So it is minimizing as well among all subsets that have its own volume. So in the end, a minimizer of this problem is an isoperimetric set for its own volume. And well, this is true now because we're minimizing among all subsets of omega, but this is true in general whenever the class among which you minimize contains all subsets of the same volume of the minimizer, okay? Because you can again use the same argument. Take a minimizer, E, okay, the class contains all subsets of omega that have the same volume of this minimizer. Well, then, when you restrict yourself to this, say, smaller class, well, the second term here is constant, so you're actually minimizing the perimeter, okay, with a volume constraint. And so you're an isoperimetric set, okay? Actually, where the set is minimizing something more general with more competitors, but it's good to know. It's some sort of, say, easy, silly corollary, okay? So this is going to be our idea. Minimize this functional in some class of competitors, which in some sense needs to contain all subsets of omega with the volume of the minimizer, or the energy, okay? And, well, what's the point now? It's take, for instance, the empty set. The empty set is zero perimeter and is a zero volume, so the energy of the empty set is zero, okay? So it's quite easy to see that there is a threshold value, which is the so-called Chigger constant, that is the infimum among the infimum of the ratio perimeter of E divided volume of E among all subsets of omega with positive mass, such that if the constant kappa you fix at the beginning, okay, is strictly less than this threshold value, than this Chigger constant, then you have a unique minimizer, that is the empty set. On the other hand, if you fix this constant strictly greater than this threshold value, than the Chigger constant, well, then you have non-empty minimizers, okay? Actually, you only have non-empty minimizer. The empty set is no more a minimum. And then there is, say, the critical value. When kappa is chosen exactly equal to this Chigger constant, well, you have the two cases somehow meshed together. You have at the same time the empty set as a minimizer and sets minimizing this ratio. And these sets are usually called Chigger sets of omega, okay? So the idea that what we do is, well, when we fix the constant kappa to be strictly greater than the Chigger constant, I can minimize among all subsets, okay? Because I minimize among all subsets, I'm ensured to find a non-trivial minimizer. This non-trivial minimizer is going to be an isoperimetric set, okay? And what we would like to do is to study the same problem, but for values of kappa below this Chigger constant, okay? But if we minimize the functional among all subsets of omega, we end up only with the empty set. So the idea is to tweak the class of competitors in such a way to prevent the empty set and in general small sets to enter in our game. Okay, so we consider the partially constrained problem, that is, minimize this energy, so perimeter of E minus kappa times volume of E with a relaxed volume constraint, that is, among all subsets of omega whose volume, whose mass, is bounded from below by pi over kappa squared, okay? That is, the volume of E must be greater than or equal the volume of a ball of curvature kappa. And, well, this class is clearly non-empty as long as you choose kappa big enough, that is, kappa bigger than or equal this constant, okay, because at that point you're ensured to have competitors. And, well, actually we will require something more. We will require kappa to be, on the one hand, less than or equal to the shear constant, and on the other hand, greater than or equal 1 over capital R, where again capital R is the radius of the greatest ball contained in omega. That is, kappa must be greater than or equal the curvature of the greatest ball contained in omega. And in this case, so for these values of kappa, our class of competitors is going to be subsets of omega whose volume is bounded from below by the volume of a ball of curvature kappa, okay? And say this lower bound on kappa, depending, say, on the radius of the greatest ball contained inside omega, comes from technical reasons that are more or less the same reasons why we restrict ourselves to dimension 2. So this is more or less our auxiliary problem. And we will characterize the shape of minimizers of these functionals. So we fix positive constant kappa and we look at minimizer of perimeter E minus kappa times the volume of E among the following classes. All subsets of omega if kappa is strictly greater than the shear constant, and among all subsets whose volume is bounded from below by the volume of a ball of curvature kappa if kappa is in between 1 over capital R up to the shear constant. And our hope that will be actually satisfied in some sense, this strategy is going to work, is that solving these two problems for all values of kappa, we will find all isoperimetric sets for volumes V greater than or equal the volume of the greatest ball contained inside omega, provided that omega satisfies some assumptions. It is, say, nice enough, and I will explain what nice enough is later on, okay? So, just a few a priori properties. Well, since your set okay, I will denote, since kappa is fixed, I will denote a minimizer E subscript kappa. And this set, as I told you, is a set minimizing the perimeter, is an isoperimetric set. Thus, it enjoys a bunch of properties such as its boundary inside the box is analytic, its boundary inside the box is constant curvature, and in particular, and this is very important, this is a key point, when kappa is strictly greater than or equal to the shear constant, well, you're actually allowed to make inner, and outer variations to the say the minimizer, and you can actually prove that the curvature is not just constant, is actually equal to kappa, okay, to the kappa you fixed at the very beginning. If otherwise kappa is strictly less than the shear constant, well, again, you can do inner outer variations if your minimizer's volume strictly greater than the lower bound we're asking to its volume. But if you have equality, you're only allowed to make outer variations to compare the energy. And thus, you only get a one-sided bound on the curvature. The good thing is that when you require kappa to be bounded from below by the curvature of the greatest ball contained into omega, well, then at that point, you know there exists a ball of volume, say, of curvature kappa inside omega, okay, whose volume is clearly pi over kappa squared, and you can compare the energy of E against the energy of this ball. And, well, by the isoperimetric inequality, you discover that this minimizer, E kappa, needs to be one of these balls, okay? So, again, you recover equality on the curvature. And this is more or less the technical reason why we require kappa to be greater than or equal to the curvature of the maximal ball contained inside omega. And all this information on the curvature is the reason why we can restrict our analysis only to dimension 2. Because when you go to higher dimension, okay, this is that the interior boundary is analytic is still true up to some, say, negligible set, closed singular set of whose Hausdorff dimension is small. The mean curvature now is going to be constant, but the problem is that in higher dimension you have a bunch of different hypersurfaces with constant mean curvature. When in 2D you only have two possible curves. Either you're a line, or say union of lines, or your union of arcs of circle with constant curvature, okay? And this is very much the key of the reason why we can tackle this problem in 2D. Okay, and then another thing I would like to do is to define maximal and minimal minimizers. And one can see that the class of minimizer, a priori you can have many minimizers, okay, of this problem. Maybe it is unique, maybe it is not, and I will give you examples where you don't enjoy uniqueness. Well, the good thing is that the class of minimizer is closed within respect countable unions and intersections when kappa is strictly greater than the threshold value, okay? When you go below, the problem is in general a bit more nasty, and you don't enjoy anymore this closure of the class of competitors. You have that the union and the intersection of two minimizer is again a minimizer if the intersection is a viable competitor, okay? So if the intersection is volume big enough to be a competitor. So in general, one usually defines maximal and minimal minimizer through some, say, I take all the union, or I take all the intersection, something like that. And in this case, you're not really allowed to do this. Okay, you would be allowed to do this when kappa is strictly greater than the threshold value, but when it is below, it is not. You're not allowed to. So we're going to define maximality and minimality in terms of the volume. Okay, so maximal minimizer is a minimizer with the greatest volume. Okay, so among all possible minimizers, you pick the one or the ones with greatest volume. And the same goes for the minimal one. Among all possible minimizers, you pick those with the least volume, and those are called minimal minimizers, okay? And it's easy to see they exist. Again, this is just direct method of calculus of variation. So the proof I gave you at the very beginning basically now works the same to prove that you have a maximal or minimal minimizer. What we will do when talking about the shape is to characterize minimal minimizers, maximal minimizer for spatial boxes, and we will be able to find actually all minimizers as a, say, suitable interpolation between the minimal and the maximals, okay? So now we will tackle the shape. I will start giving you some results, and to do so I want to start studying a very special case, okay? That is the critical case. So when you fix kappa, the constant, to be equal to the Cheever constant, which I recall to be the infimum of the ratio perimeter of E divided volume of E among all subsets of omega whose volume is strictly positive, okay? Let me define this set, which is called the inner parallel set of omega at distance t, that is the set of points x in omega whose distance from the boundary of omega is greater than or equal to t. Okay, so it is at least t. This is a closed set, is a closed subset of omega. Now, the good thing is that the Cheever problem has been studied a lot in the last 20 years, and we know we have some nice structural theorems. We know that if the box omega is convex, or it is a strip, and by a strip you should more or less imagine a rectangle which you're allowed to bend a bit by keeping the width constant, more or less. Okay, so if your set is either strip or convex, then we know there exists a unique Chigger set, so a unique minimizer of this ratio, and it is given, it has a very nice geometric property that is this set E is the Minkowski sum of the inner parallel set at distance r with a ball of radius r. That is, in other words, you take the union of all the balls of radius r contained in omega. This is exactly the same thing as saying you take that Minkowski sum. It's the union of all the balls of radius r, where r is nonetheless the inverse of the Chigger constant. Okay, so if you know the Chigger constant, we know who the minimizer is. It's the union of all the balls with curvature, the Chigger constant. Okay. Well, actually, this characterization tell us something more. They give us a recipe to actually compute the Chigger constant, because they tell us that R needs to be the unique positive solution of this equation of volume of the inner parallel set at distance t equal pi times t squared. Okay, so the idea is the following. You take a convex set or a strip, you solve this equation, which you ensure to have a unique positive solution. This positive solution is the inverse of the Chigger constant, okay? Great, so you know what the Chigger constant is. And now you take all the balls of radius r contained inside your set omega, and that union is the unique Chigger set of omega, okay? This, I believe it is a very elegant and nice theorem, a very nice characterization, but what bugged us maybe now it's almost 7 years ago or something like that, is that if you were to draw a Venn diagram of convex sets and strips, well, these two overlap, but they're not contained one into the other. So the question is there a larger class that contains both convex sets, both strips, for which this theorem holds? And this is basically what we proved in our very first paper. So let me give you a necessary condition that we introduced ourselves. We say that a set omega has non-x of a given radius r if the following condition holds. Whenever you pick two balls of this radius r contained inside omega, you can drag one onto the other in a continuous manner without ever exiting the set omega. Now, this formally means there exists a continuous path starting from the center of the first ball, ending on the center of the second ball, such that whenever you take any ball of radius r centered on any point of this curve, well, this ball is contained inside omega. And the interesting thing is that you need to require this condition for the radius given by the inverse of the Chigger constant. Otherwise, the characterization that the Chigger set is the union of all the balls of that radius fails. And it can fail in both directions. For instance, if you take the example on the left, an unbalanced dumbbell, so say a ball of radius 1, a ball of radius 2/3, and you join them through a thin tube, it can be seen that there is a unique Chigger set that is given by a very small perturbation of the ball of radius 1. Okay, so the Chigger constant is going to be very close to 1/2. If you were to take the union of all the balls of this radius, very close to 1/2, you would cover not only the bigger ball of radius 1, but as well the ball of radius 2/3. Okay. So the union of all the balls of this radius would strictly contain the Chigger set. Then there is this other example where the quality fails in the other say inclusion. This is basically a bow tie. So the idea is that you start from a rectangle and you start pinching the the midpoints of the long side, you pinch them closer and closer, and if you pinch them enough but not too much, you end up in a situation like this, where the trigger set again is the grayed out thing. But if you were to take the union of all the balls of radius, the inverse of the trigger constant, well, what you would end up would be this shape here and this boundary here, okay? So you would have that the trigger set strictly contains the union of all the balls of radius, the inverse of the trigger constant, okay? So you need to require this condition for the radius given by the inverse of the trigger constant. And what we proved is that basically, more or less, this is also sufficient. And by more or less, I mean we have this following theorem. We take a planar domain, we take R to be the unique positive solution of mass of the inner parallel set at distance t equal to pi times t squared if omega has non x of radius r, okay? And so this is the necessary condition we just talked before, and then we require on top of this, say, a topological assumption that is omega is a Jordan domain, that is its boundary is a Jordan curve, and okay, this curve has zero area, okay? I mean, is not a space filling curve, so it's not say piano-like curve. Piano curves are not Jordan curves, but there are Jordan curves that fill the space. So omega is non-x of radius r, omega is a Jordan, the boundary of omega is a Jordan curve, is a non-space filling Jordan curve. Well, then the trigger constant is the inverse of this radius r. And now we cannot talk anymore about the unique trigger set, but we can say that the maximal trigger set is given by, again, the Minkowski sum of the inner parallel set, the distance r, with a ball of radius r. That is, again, the union of all the balls of radius r. Now, what about uniqueness? As I told you, we can only speak about maximality up to this point, but we also proved that if this set equality holds, that is, the inner parallel set at distance r coincides with the closure of its interior, then E is also minimal. And this actually means that E is the unique minimizer. So this is basically the characterization that we had for convex sets and strips, proved for a much wider class that is basically sharp. You cannot really do any better. And again, it works like this. You solve the equation, okay, omega needs to be a Jordan domain whose boundary is a non-space filling curve. You solve the equation. If your omega has non-x of radius, the unique positive solution of this equation, well then this unique positive solution is the inverse of the trigger constant, and the maximal minimizer is given by the union of all the balls with this radius. Okay, so again, we have basically this recipe moves from convex sets and strips to this much wider environment. Okay, and I believe this is a good point to stop the first part of the talk. You have now some time to digest this structure, because this theorem is basically what we will be building upon in the next part, when we will tackle the general structure for general choices of kappa.